Hi, this is Group 1, and this is our term project presentation for the design project to create an unmanned aerial system. During this presentation, we will introduce the group members, the purpose, customer needs, design metrics, a UAS comparison, the final design, flight test results for the final design, and a summary. Our team members are Elizabeth Talburt, Devon Barragan, and Soemoe Oo. The purpose of this project is to aid the National Forest Service in exploring options to use an unmanned aerial system, or UAS, to locate missing hikers. Our team conducted experiments to support the National Forest Service with designing a UAS that fit their needs. The customer needs were as follows. The National Forest Service wanted a slow-moving vehicle with a small size that was able to operate at low altitudes, less than 300 feet. It needed to be easily transportable, able to navigate low mountain terrain, able to operate under a wide range of weather conditions, and able to operate during the day or night. From these needs, we came up with design metrics. So before exploring the options with the Embry-Riddle Hub Assembly Lab, we came up with these design metrics. So the vehicle should weigh 50 pounds if it were to be anticipated to be moved by a one-person team, or if a two-person team were to be moving the vehicle, it should weigh about 100 pounds. And this weight limit was based off of a study by the Human Factors and Ergonomics group that concluded that 50 pounds was a reasonable weight for the average person to carry. The need that this constraint met was that the vehicle needed to be easily transportable. The dimensions of the vehicle shouldn't exceed 4 feet by 5 feet. If the vehicle is larger than these dimensions, it should have the ability to be folded to fit within this constraint. And if the vehicle couldn't be folded, then it should be able to be disassembled and reassembled in a reasonably easy manner so that it could still remain easily transportable and have that small size that the National Forest Service was looking for. The vehicle should also be waterproof, and that is to address the ability to operate under a wide range of weather conditions. It should also have high intensity lighting using 1,000-watt LED lighting or an infrared camera system, and this was to address the need to be able to operate during the day or night. It must not go over 100 miles per hour, and this met the need of it being a slow-moving vehicle. Shuttle radar topography mission, 1 ARC. It's a global elevation data system that offers worldwide coverage of void field data at a resolution of 1 arc second, so 30 meters, and provides open distribution of high resolution global data sets. So this would address the need to operate at low mountain altitude. So if there was mountainous terrain, then the UAS should be able to know what the terrain is and have information on the topography of that terrain. And that same system could be also used to meet the need to be able to navigate that low mountain terrain. After studying what was available through the assembly lab, we revised our metrics to the following. We kept all of them except for the last two. So instead of having that system showing the topography of the landscape, we replaced it with a laser altimeter, and that would meet the need to be able to operate at low altitudes. So that laser altimeter would feed back information to the UAS and to the controller of the UAS on where that vehicle was with respect to the ground. And it would have manual control, and this would allow the system to be navigated through low mountain terrain. We found that during experimental flight tests, it was hard to have a predetermined flight path using automated control, and this was due to the fact that it was mountainous terrain, so sometimes the altitudes varied, and there could be obstructions like trees, and if the path was predetermined, then the UAS would not dodge those potential obstructions. Using manual control, combined with the fact that it's a slow-moving vehicle, allowed the UAS to have that flexibility to navigate through different terrain and be able to survive a flight through the mountains. So here's our UAS comparison. This chart, we compared all the different UAS systems that were available in the assembly lab. So that was the Condor octorotor, the Razorbill quadrotor, the Harrier quadrotor, the turn fixed wing, and the Gannet rotary wing. And we compared the weights of these systems, their maximum weights, and the weights when a different power supply was put in. So here's the summary of what those weights were with different power systems. And it can be noted that the Gannet rotary wing is over 100 pounds, so that was immediately excluded as one of our design options. The turn fixed wing was 22 pounds with just the vehicle and the power source, not any other systems in it. And we found that the lightest and most easily transportable vehicles would be either the octorotor or one of the two quadrotors. Ultimately, we decided on the Condor octorotor, and this was due to the redundancy in its motors. So a quadrotor only has 4 motors, while an octorotor has 8. And if there is a motor failure, say in hazardous weather conditions on a quadrotor, one motor failure will cause that vehicle to crash. If you have an octorotor, since there is redundancy in the engines, if one engine were to fail, then the vehicle would still be able to be used and flown. If 2 engines were to fail, then the vehicle could still be flown and used. And this is due to the redundancy in those motors and having the 8 motors available just in case some of those motors fail. And that gives it more flexibility and gives it the ability to operate under various weather conditions, be it windy or rainy, or even if there was some sort of obstruction that it ran into. So with our UAS comparison, this is a summary of why we chose the octorotor. It fit our team's metrics for the National Forest Service rescue vehicle. In our next section, we compared the subsystems of the octorotor to yield the optimal combination of sensors, camera, antenna, and other subsystems. Our final design, so we had 3 designs that we varied the different systems to test the Condor octorotor, and we settled on design 3. So design 3 had 8 black electric motors, manual control, an infrared sensor with gimbal, laser altimeter, dipole antenna, ERA 5600 battery, a GCS, so ground control station trailer with a large dish, IMU, which was an internal measurement unit, and a GPS system. This is a screen capture of our flight test. Since it was a manual control, it was easy to navigate through the mountainous terrain, and highlighted in a red box is the silhouette of an animal. It looked like a bear. And because we were using an infrared sensor, it was easy to spot the silhouettes of animals. So it would be easy to spot the silhouette of a person. And this is due to the fact that the heat signature of the terrain is dark. And the heat signature of, say, an animal, or as you can see in the background, a fire, is bright white. So the contrast between the darkness of the background and the bright white signature of any living thing that it happens to be in the forest will allow us to have clear sight if there was a missing hiker and if they were somewhere in the forest. So this is a summary of our findings. So we used the Condor octorotor, and the 8 black electric motors fit metric, fit metric 6 and 7. It allowed it to be able to operate at low altitudes, navigate through low mountain terrain, and it also met metric number 3, in that it could operate under a wide range of weather conditions. And again, that was because of the redundancy in the motors if there was a motor failure due to weather conditions. The manual control also met metric 7, which was the ability to navigate through low mountain terrain. The GCS trailer with large dish also met needs 6 and 7, so being able to navigate through that mountainous terrain, you need a wide range for your signal, and signal transmission with the GCS trailer was very strong. The infrared sensor allows the UAS to be able to operate during the day or night, which is metric 4. The laser altimeter meets need 6, which is the ability to operate at low altitude. That laser altimeter provides feedback to the UAS and to the person controlling the UAS. It provides information on how far that vehicle is compared to the ground and if evasive action should be taken if the vehicle is flying too low. The GPS module allows trackers' locations to be precisely noted. The battery has to do with the fuel, so if it were to be operating under an engine that required fuel, then that would have an impact on the weight capacity. And the IMU, so the internal measurement unit, addressed the need to be able to operate under different weather conditions. So that would provide any information on if there was some sort of damage or errors in the control system or systems of the UAS. The IMU would pick up on that and be able to send feedback to the controller. So they would note that if there's any changes to the UAS because of rain or the weather, that information would be available to the person controlling the UAS. And references for our project are included. So thank you for listening to our presentation, and I hope you enjoyed our design project.